We go through them. So I'm Andy Warfield. I'm the CTO of Coho Data, and this is the second of 4 sections in the Storage Field Day 6 presentation. This is around the convergence between storage and network data paths. I thought you were sighing already, but it was just your your carbonated water. Hopefully this is kind of an interesting thing, and hopefully it drives a point home. Storage systems for like 30 years have basically involved 2 types of media, right? A huge amount of spinning disk and a very small amount of proprietary battery-backed RAM. And the reason that you bought enterprise storage was because there weren't really commodity products for the proprietary battery-backed RAM. And you wanted a stack that knew how to use it and was going to give you all sorts of assurances about durability, right? That storage vendors today are still implementing the same systems that they've been implementing for, protocol-wise, 10 to 25 to 30 years. And there's nothing wrong with that, right? But it's important to realize the consequences of the way that the media that we build storage systems with is changing. So, we work with NVMe flash, right? There's lots of back and forth around like, why would I use NVMe? I could use like a pile of SAS or SATA flash, right? That's a good way to build a shelf of storage. This is not a black and white answer at all, right? The latencies that you see, the vendors selling SAS and SATA flash today, as a matter of course, right, it has nothing to do with the interfaces, don't spend as much on the FTL, right? And so it's a smaller sale, and they want to sell a disk that costs small hundreds of dollars and not thousands of dollars. And so write latencies especially are significantly longer on these than on these. And so what you see when you have products that are built on top of these is generally there's a bunch of battery-backed RAM, right, to handle the write path. And so you have this small write buffer, and then you go onto the large number of SAS or SATA drives for the read path. These are just decisions that you make in designing a system, right? The thing that we saw when we moved to NVMe was that we could build a completely commodity system without having to pay out for NVDIMMs, which weren't ready at the time, because the latencies on PCIe flash are in the small hundreds of microseconds range, right? They're fast enough that you can just go straight to flash with your writes. Yeah, sorry.
Or go on the other side.
I can stand over here. Yeah. Does that work?
Yeah.
There are a couple of other things to realize about this sort of like stratification of these things, right? A spinning disk at 10 milliseconds down onto emerging NVDIMM technology at tens of nanoseconds is a million-x difference in latency. I've worked with computer system software for my whole career, and I've never faced a million-x latency difference across components in a system. It is a nightmare, right? It's really hard to engineer for this. When you fall off the end of a cliff between this and this, you really fall off. This is the distinction between RAM and disk in a traditional, this is like paging, right? But for non-volatile, this disparity has never been there. The cost difference is also really interesting to look at in that these NVDIMMs are $40 a gig, right? And they, use a lot of power and have all sorts of, consequences on that side. But for that million-x performance speed up, right, it's only a 400x difference in price. So necessarily, right, and obviously we should just put all of our data onto NVDIMMs, right? Duh, right? And sarcasm, hopefully. Right, let me kind of go a little bit further with this, right? It's expensive and performance dense, and I kind of went through this before. And so getting efficient sharing on this stuff ends up being really hard. If we look at the network side of this, there's some pretty cool stats, right? So this is the sort of generational shift of network interconnects. And a really sort of useful stat to draw to this is these are small packets, 64-byte packets, the number of nanoseconds that you have on the host to process a packet, right, coming through the machine is falling really dramatically, right? It's fallen by 1,000x between fast Ethernet and 100 gig. Another way of looking at this 100 gig number is that for small packets, you effectively have 40 cycles per packet, 40 CPU cycles per packet to process a request. Now, even if you have local storage, you are going to replicate it, right? And with performance-dense storage, you're going to remote a bunch of your accesses anyways. And so the network is going to be involved. And at 40 cycles per request, you are totally hooped, right? Running the application as well there is you're never going to saturate, these devices. And this is doing very little work at this point. So you have to really think about how you're going to fit the stack in. And so let me talk through two ways that we use the stack and the way that our stack is evolving. So here's a way to think about the Coho Stack. We've got this SDN switch and a bunch of clients out here. And then let's say I've got a pair of our microarrays, right? And these guys each have a set of wires in like this.
When you say 40 CPU cycles, you're talking at the SDN layer per packet?
No, at the end host.
At the end host, okay.
Yeah.
Right.
That's like a super lower bound, right?
Yeah,
I'm not trying. I'm being dramatic. So we can do active-active redundant switches, but they get really messy to draw. So let's just assume the single case here, right? So you can think about the stuff that we do with the network kind of as sort of two fun components. If I think about what happens basically from here to here, right? This is what I would call a distributed TCP endpoint. And down here, I'm going to draw, imagine that we have just a shadow of that switch, right? This is a virtual set of wiring, but basically because of the fact that I have control over the switch, right? This is the same physical wires, but I have a virtual L2, right? I have an interconnect on that same network, right? So this is my virtual L2 data path. Or now, this architecture is not fundamentally different from a lot of other distributed storage systems, right? In fact, there's like two significant systems that have been built over the past decade or so that have used InfiniBand as a backplane to do this stuff. The observation here is really that with commodity Ethernet, we can do a good job of this stuff, and we can get a lot of value with fewer wires. These are two places that we do a bunch of interesting work. If I talk about the L2 end of this first, do I want to do this? I do. Here's a way for me to illustrate some of what happens down here. Can I erase this? Don't get too distracted with that graph yet, because it won't make any sense until I show you something. The NIC vendors realized quite a while ago that they were building devices that were faster than the CPUs that ran them. And as we started to see multi-core CPUs, we saw the NIC vendors take advantage of that by presenting the NICs up in MultiQ, right? And so what you would have in a server is basically you'd have a physical NIC, and you'd have some degree of on-host pathing or flow steering to balance the request load across multiple cores on the CPU, right? This is not super new, but it's something that we're still actually evolving interfaces for, right? It's changing really quickly. So on your Xeon, for example, right, if you have 4 actual cores, right, what you'll see on this are send and receive queues. I'm just going to draw one that allow traffic to be steered across these cores, right? And so the idea here is if you're building a really, really fast web server, for example, you'll do 5-tuple hashing or MAC address hashing, right? Flow hashing. Receive side scaling is the term that these guys often use to distribute the TCP flows off of these onto individual cores, right? And so now you can involve more cores in serving the requests. Well, surprise, the NVMe guys have realized the same thing, right? And this is pervasive in storage, right? Network pain becomes storage pain a few years later. And so what you get with NVMe is an equivalently MultiQ implementation, right? These guys are building interfaces that allow you to register command queues, arbitrarily many, right? Often into the thousands if you want to, to tie these directly off to these cores. Right? Now, to illustrate the cost of screwing this up, right? And the sort of lesson that I'm trying to draw out of this is that it's really difficult to take these technologies and just wire them into an old storage stack. I got one of the intern guys on the engineering team that's been working with some of this stuff to do a really quick demo this week on this to give you some numbers. And the test that he ran is just saturating a 10 gig NIC on a single core, right, at small packets. And he can't quite get there, right? He gets to about, I think the number was around 10 million packets per second. So we add a second core, and we're able to drive 12 and a bit million packets per second off of this. There's no storage involved, right? This is just really emphasizing the CPU pain on these things. And with that, we are close to the sort of theoretical maximum on the NIC at 10 gig, which is around 50 million, right? But there's overheads and stuff involved. And then what we did was, so the code that's running here is just simple, like reflection code, right? It's like a ping server. And we drive it up to this really high rate. And then we ran a second experiment where we added a count plus plus on a variable. So we just read a value from memory and we incremented it. So a read, increment, and write, right? It's like a very, very small number of instructions. And when we run that on two independent counters, we get this number, right? We get our saturation number. So we're doing the work here, but we have two independent pieces of memory for the two cores. When I make that one global counter across these, I get a 20% reduction in performance because the CPU cache is trying to bounce that piece of memory back and forth across the cores. This is not safe yet because I haven't locked the value. Right? Both of these cores are going to be reading it, incrementing it, and writing it, and they will step on each other's values, right? So this is not how you would build any useful shared data structure other than maybe a like sloppy performance counter, right, in a storage. So you wouldn't use this for like file locking or anything like that. When you add a lock, you lose about another 20%. Right? So you're down 40% on a single piece of shared data across the cores. Now, how much shared data do you think there is across the access paths in your file system implementation? Spoiler alert, lots. And so you really, really have to be cautious with this end of the system. And so the idea that we have around doing this bottom layer where we carve up the flash into just isolated chunks, right, and push that out is a really fundamental thing, right? It lets us focus on this data path that is exposing a subset of this like that and a different subset of this like that, except it's not partitions in the sort of traditional sense. It is a coarse-grained allocator, right? You're allocating megs at a time and feeding them through. And we actually push the addressing of this memory, right, of this flash, out to the network. And so the way that you avoid contention across these cores is to advertise the fact that, I know that this core is serving this flash, right? So I'm going to address this channel as a single thing, so when the request packets come in, you don't get the thing that you would otherwise get in the system, which is it comes into this core, but actually this is the one that owns that stuff and has to forward it across. So there's like a huge value to working directly with the network to integrate some of this stuff. And so the way that we're moving to implement this is we already have a user level stack, and we're very cautious about not shuttling payloads through the kernel, right? So in our stack today, what you see is a kernel user divide where the read and write payload traffic basically does this, but the request chunks of things, right, the offsets and the sort of header stuff comes up like this and is heavily batched. So we avoid copying the bulk chunks of the data, and this lets us get really good performance. But as we get into these higher rate devices, even this is problematic. And so what we've done is we're working with something called the Intel DPDK, which is one of a set of Datapath kits largely used by people who build routers, right? It's a networking tool. And we're moving the drivers that sit down here to live up here. And so both the NVMe driver and the Ethernet driver actually move into user space, right? So the user space single-threaded core is responsible for taking data from a device to a device, right, with no involvement of the kernel. And it's a very, very efficient way of utilizing the resources on the machine, but it needs a bunch of kind of fun engineering on the stack, right? So this is the class of problem. Yeah.
Is anybody else doing this?
I don't know. I know of researchers that do stuff like this. There have been a bunch of really interesting papers out of Dave Anderson, for example, at CMU. I can send you pointers to that stuff. Dave Anderson has this great paper where they basically build a drag race car of a storage server, right? It's RAM, it's a network, how fast can we go, right? Assuming NVDIMM, and I think they post numbers in the neighborhood of like 7 million IOPS from a single box, right? It's squarely around shared nothing at this path. Now,
So you believe you can do 4 times what normal systems could do with an NVMe? I mean, that's kind of numbers you're thinking about here?
that's certainly what we're pushing toward. And this doesn't need to be NVMe, right? I'm trying to anticipate the arrival of NVDIMM, right?
Yeah.
NVDIMM has arrived barely, right? The wiring, one of the challenges with NVDIMM is, they've got the power side of it worked out, right? The vendors are plumbing in the power for these devices to charge and fire the supercaps to drain, but they don't have the CPU integration to deal with write buffers off the CPU. Right, so the CPU doesn't know how much of the data that you think you've written to RAM is in RAM.
Yeah.
And so when you lose power, the RAM is not crash consistent, right, to go back to that term. And so Intel actually just this week, I think, announced a set of instructions to force memory ranges to RAM, right, to basically, do range dumps to RAM to get that consistency. And so again, the storage vendors are going to have to write their systems to anticipate those things.
Are you actually setting affinity to the cores then?
Yes.
And when you put a dual proc or more in a server, does that make any difference to this?
Yes.
Because now you've got
Yes,
all kinds of
absolutely.
other memory things.
Absolutely. And so it's a bunch of that kind of balancing. Now, there are 2 kind of neat things that kind of follow from this. I'm going to go way over time.
Good.
There's 2 consequences to this, right? I've built this shared nothing. You can, the right way to think about this is like a volume management layer, right? This is like a abstraction that is really just carving up the disk. It's like a hypervisor, right? It's carving up the resources with as little overhead as possible and really trying to let the system manage, placement in a compute efficient way. Now, when you think about what it means to build stuff on top of this, right, let me give you 2 really specific examples. One is NFS namespaces, right? And NFS namespace is a complicated data structure, right? It has all sorts of sharing problems. And so what you want to do with an NFS namespace is avoid sharing across cores wherever you can. And so the way that we build metadata type structures on top of this, and this is, I'm telling you about stuff that is partially going into the stack and is work that we're doing. Last year when I talked about this stuff, I talked ahead of what we're doing. So this is bleeding edge, and please don't take this for anything other than that. But the implementation that we've been doing on this side is you take that NFS namespace, right? So maybe I'll draw it as a tree. The correct way to do this, and this is like a really, really important thing with these systems. When system designers are constrained on resources for metadata and for scale, they often fall over to sort of vague algorithmic approaches to solving the problem, right? So RAID is an example of this. I don't want to keep metadata on where every single piece of chunk data is on the system, so I use RAID as a transform, right, that takes me there. And it's very space efficient in terms of avoiding metadata, but it risks things like hotspots, right, because you can't change the transform. In object storage, a really frequent technique is consistent hashing, right? So you have a hash function, you erasure code your data, now you need to know where to place it, so you build a ring or you build whatever kind of address space, you hash the thing and you throw it at the address space. It does a really good job of scaling and it throws away locality altogether. And so when you want to build a data structure on top of it that actually benefits from locality, you end up with trouble, because if you're hashing each file in a directory of an NFS server into an opaque address space, and then you do a directory list, you now have to send an RPC to every single node in the system to go and fetch that data back, right? We wanted, with these latencies, to preserve locality, right? We wanted to be able to keep that control, to keep the data close together. And so the way that we approach this is we build distributed tree-like data structures. This is the NV, or the NFS namespace example, where this is all actually controlled by a single node. So we're going to put this whole NFS namespace on one core of one server. and we're going to let you send requests to it. And if two people try to access the same file, that's fine because they don't have to lock across cores. We don't take that expense. But we're going to watch this to see when it redlines. And as soon as it redlines, I'm going to cleave this tree in half. Right? I'm going to decide to go, actually, the homes subtree is in trouble, or represents about half the load, and I'm going to give that now to a different core, right? Or even better, a different server in the cluster. And now I'm going to scale the thing up like that. And what I've done is I've preserved the locality over these things. This delegation is a control path thing, right? The decision to cleave the tree is something that you do at the order of tens of millions or billions of requests. But you're keeping the data together, right? Which means that you can move things like the subdirectory being accessed over to the host that's accessing the subdirectory, right, to try and keep things closer together. Now again, I have to be cautious with my terminology around client and server because for us there's really two clients, right? The ESX host, right, or the NFS client is the client that you think about when I say client. And I can't change that one, right? So to me, the sort of really thin virtualization layer on the flash is the server. And when I talk a lot, the client I mean is actually our NFS server, right? I don't think it will be like that forever. We're increasingly seeing applications where we can get around NFS, where the customer is willing to take on that library that our NFS server links to and goes in there. So the system is being designed to assume, applications that directly support the storage, because NFS is a huge problem, right? And so is iSCSI, and so are all these other protocols as an indirection. And so that's kind of where it goes. Last thing about this is that by delegating all of this stuff off to these writers, right? So I am going to allow this core to do everything from allocating new space on here, right? It's going to go and ask for new space on the flash. It is out here on the client side of this, right? So this side, this guy is actually implementing things like snapshots and replication for the objects it's accessing, right? I've delegated all that control off, so it's not a central controller. And so what you end up with is basically a three-party trust model for storage, right? You have the disk, right, or the piece of storage that's being virtualized. This is a terrible term, but I have trouble naming this. We were calling these network-attached disks, which acronymized really poorly. And then you have your client, right, which is taking these chunks and implementing things like snapshots and sparse address space and so on. You're going to let this client have very, very extreme control over the data that's on there, and now you have to have this central notion of trust in the cluster, failure response and things like that. And so the disk is responsible for isolating clients from each other, right? It does the thing of saying you're not allowed to access this chunk of data because you didn't. The client is able to implement all of their stuff, and that's a library-based approach. And then there's basically a third party over here that does things like health monitoring and asking disks to do things like disk-to-disk recovery, right, if you lose stuff. So the system kind of breaks out in three parts like that. How am I for time? Okay, I'm going to really, really quickly, now I'm 2 minutes past when I wanted to finish this section. But I'm going to tell you about one last example because I think it'll be interesting to you. The last example is the other half of that switch diagram that I showed you, which is the distributed TCP implementation. Now, the way that we originally used the switch was really naive and incredibly effective. You've got the SDN switch. You have a bunch of clients coming in like this. You have no control over the code on the client. These are the ESX boxes, so they get programmed with an IP address for the NFS server, right? And you want to balance that traffic. And so you have a bunch of microarrays down here, and you wire this like this, right? This is all over a shared Ethernet. And using SDN, using OpenFlow in particular, I can stick rules into the forwarding tables on this switch, right? The thing that is cool about SDN is eventually that maybe you will do all sorts of crazy stuff with your data center network. But the thing that's cool about SDN to us is that we can program the switch. Right? We can take advantage of these chipsets that have been getting really great for 10 years and have been totally opaque to developers. And so what this specifically means is I can give each of these hosts the same IP address for NFS. Right? I can do the thing that you should never do in your network. And name them all the same thing. And when a client goes in to connect to that NFS server, I can take an exception in my OpenFlow controller, right? So we have a controller here that goes, wow, I've never seen this connection before, where should I put it, discusses with the system, decides where to go, and fires it off onto one of these nodes. And I can manage that TCP flow through its lifetime, right? So this isn't DHCP or DNS trick. I can actively move this connection around, which means as the system scales out, I can redirect it to a new node. So the way that I have always sort of thought about that is I'm taking the TCPIP stack that runs on these, and I'm moving some of it out onto the switch, and I'm turning this into a distributed TCP endpoint. Right, these things also have their own IP addresses, right? They also live on a private L2 for the backplane, right? But for this service, there's basically a facility in here where my NFS server application can listen to a port on an IP that is a cluster shared IP, and the switch will collude with them to steer traffic to it. So they each have a slice of the TCP endpoint. Now, what we really wanted to do originally was have the switch look inside the TCP stream of NFS traffic, right, and pull out the read request and send it to the host that had the data on it. You can't do it right now, right? The reason you can't do it is that you have Ethernet frames that are fixed size, and your TCP stream is continuous, and your NFS read and writes end up being in the middle of this. And the chipset on the switch that's capable of making a decision like that can only look at the first bunch of bytes of these things. And so it can't do packet inspection at a level that would let you make these forwarding decisions. There are other problems like the fact that XDR, right, the SonarPC protocol that NFS uses has data dependencies that mean you have to read one part of the packet to figure out where the next part of the packet is. Switches also struggle with that. And so instead, we steer the whole thing down. And this leads to the too hot problem. Right? So we can move the streams around really, really effectively. We can move requests close to the data that they're accessing, and since we have locality, that ends up being a win. But you're going to have remote data. And so how can we solve that? And the way that we solve that, or that we are prototyping right now and hoping to roll in the first half of next year, is that because this is a distributed TCP endpoint, if I take a flow in here, and I know the data is over here, instead of going, can you please send me the data and send it back, I can prepare the reply packet header here, and I can send it like an envelope there. Right? And so I build the TCP reply, I send it over here, and I let this host reply to the client. It's like triangle routing, basically. So a request comes in like this, goes over there, goes out. Right? Another request comes in, right? And sorry, back to the same client, hopefully, not triangle receipt. And so on. So we're really doing some pretty fun stuff at the switch and endpoint level. And part of the win from this is the fact that we've pulled the network driver and the TCP stack up into the application. Right? We're not stuck with Linux's TCP stack. We're able to actually integrate directly with TCP, which means that we can do things like control incast, which is a big problem with storage systems, right? We can do end-to-end congestion and flow control across the cluster, right? There's a whole bunch of cool stuff that this opens up when you go in this direction.
Physically, when you're sending a request from one of the microarrays to another, it came in on the wrong microarray and you need to send to another one to fetch the data. That's actually going back through the SDN switch.
It's the switch is involved in all of this stuff. Yeah.
Right. So physically, the packet has to go back out through that switch and into the other microarray. Logically, it's just going from one array to the other array.
No. So the distinction is, yeah. So I drew that line incorrectly. So in the like current world, right? And this is true of anything that does like forwarding, request read forwarding. It has to come in here. It has to go over the switch to there, right? It has to come back, and then go out, right? And this isn't at all the end of the world, right? In particular, since we've done this IP load balancing thing, we're already getting way more exposed throughput than any other NFS system built gets, right, transparently. Because we're getting 40 gigabits here, and we're getting 80 when you add another one, and so on, right? We've got that scale. But it would be nice not to be redundantly sending this data. And so by doing this next step, what you get is the client request comes in, it goes over to there. So there is the second transition, but the reply goes right out. And the interesting thing here is twofold. First of all, the bulk data movement only happens once, right? So that forwarded request is small on the read path, whereas the reply is big. And secondly, the interrupt rate for packet processing falls in half because this host isn't having to read the reply traffic as well as the, right? So it's less work. And so how does that actually play out? This is local access with no forwarding at all, right? When you do the forwarding, you basically fall slightly over half. And with this triangle routing stuff, you reclaim back up to almost full performance, right? You're above 80%. So the throughput that you can offer from the system is considerably higher.